African cities, and mainly we are going to talk about 3 cities in West Africa. We are going to talk about Ouagadougou, Dakar, and Lomé in Togo. So I invite those who are here also to register for that important online seminar. And the membership, I think that some people who are here, some participants would like to know how to join the African Society for Air Quality. It's totally free. You just have to get to our website and send us an email, okay, and express your interest to join the group, and we will accept you as we have done for many people. Maybe before the end of this session, I will also put the emails where you can express your interest to join the society. So this is what I can say for now, Dan. Thank you very much.
Thank you, Bertrand, and looking forward to the seminar on Friday. Okay, so I think I'll go ahead and start with the presentation. So allow me to share my screen. And let's go this. So hopefully you're seeing my screen. And if you have any questions, you can pop them into the chat and I'll try to answer them. We'll definitely have time for questions at the end, but I'll do the best I can at monitoring the chat and presenting at the same time. So, okay, we'll get started. So this is low cost air quality monitoring using, calibrating, and ensuring quality from low cost sensors. So like I said, I'm Dan Westervelt, filling in for Mike Giordano, R. Subramanian, and the rest of the AfriqAir team. So as many of us probably know, air pollution data is very sparse in many places in different countries in Africa. And the data that we do have from other sources, such as models and satellites, tend to indicate that the air pollution is probably more severe and dangerous for health. And so this figure on the right is just sort of outlining that. It's showing on the y-axis the PM2.5 annual mean concentration. The different dots are different regions of the world. And then on the x-axis is the number of PM2.5 monitors per million people. So ideally, you want to be on the bottom right of this curve here, because you want a lot of PM2.5 monitors and you want low PM2.5 concentrations. So you can see there's some blue and black dots here, which represent Europe and North America, where there are a lot of PM2.5 monitors and also fairly low concentrations. If we go over to Africa, the red dots are Africa, and especially if you look at Western Africa here, we have much higher PM2.5 annual mean concentrations. This is from satellite estimates, so it's not necessarily the most vetted and accurate data source. So we have high concentrations, 100 micrograms per meter cubed, and relatively low number of monitors per millions of people. You can look at other parts of Africa as well, Eastern Africa, Middle Africa, Northern Africa, all sort of along the same story there. So low-cost sensors are possibly an option for getting high density air quality data, especially in places where there's not a lot of data available. And this is because the reference monitors that are typically used for environmental and air quality management in wealthy countries are very expensive, somewhere between at least $10,000, but often more than $100,000 just for a single instrument. And so these exist, a lot, for example, in the US, but even there, the distribution will never be enough to have neighborhood level or hyper local information about air quality. So it's not just in the global South, I would add. Almost everywhere can benefit from low cost sensors. You know, this low cost sensors, obviously in the name, they're much cheaper, and that's their advantage. However, the data quality is possibly not as good as the reference monitors. And so it's a scientific challenge to then figure out how do we get useful data out of these low cost sensors. And that's kind of what we'll talk about today. So the outline, we'll talk a little bit about the low cost sensor principle of operation, so how they work. Then we'll talk a little bit about linearity and limits of detection, and then a little bit about calibration setup, calibration models, and then some final remarks. So this is some of the figures in this talk are based on a paper first authored by Mike Giordano. I'm also a co-author on it. And so you can see the link for it there. We can share it after the meeting if you want to take a look at it in more detail. So let's talk about particle sensors first. So the principle of operation is light scattering. That's pretty much what the sensors are actually measuring. They're not directly weighing the particles. They're not directly, getting the mass in some sort of like filter or balance method. Instead, what they're doing is just measuring the scattering of the particles. So if you have some kind of light, shining at a particle, some of it is going to be absorbed, some of it is going to be scattered, and then some of it is going to pass through and be neither, scattered or observed or absorbed. Sorry. And the physics of the optics of scattering and absorbing of spherical particles is described by Mie theory. You can look more up on that if you'd like, but what it says is that basically, the particles interact with light in two main ways. They can absorb light or they can scatter it. And absorbing light is not something that's easily measured by PM2.5 monitors. This is a very difficult measurement. And if you have a lot of absorbing aerosol in your low cost sensor, chances are your low cost sensor is not going to detect that. Sorry, if everybody could mute themselves if they're not speaking, that would be great. All right. Thanks. So, particles that absorb light, won't be detected very much by low cost sensors. That means if you have a lot of black carbon, for example, in your aerosol, your low cost sensor might underestimate how much mass is actually there. Particles that scatter light is much easier to measure. So the scattering can happen in all kinds of different directions. Rarely is it sort of scattered completely in the reverse direction. It's often, as depicted in this figure here, some 100-degree angle or 90-degree angle or something like that. So not sort of a direct reflection. And this is much easier to measure by low cost sensors, and this is how they basically operate. So what you have here is a couple of schematics. On the top, we have a potential low cost sensor schematic where there's no particles. So this is relatively clean air. And these arrows here at the top, you would have a fan to aspirate and draw in air through this chamber. Okay, and in this chamber, you have your light source. Oftentimes with a low cost sensor, it's a small laser. You may have some kind of focusing lens, and then you have a photodiode, basically, that detects the light that's scattered and then converts it into an electrical signal and voltage, and then that gets converted into your PM2.5 mass, or your particulate matter mass. So when you have no particles in the chamber here, in this top example, you don't get any signal in the photodiode. Particles come in, you have a signal that could look like this. So, when particles are present, the photodiode signal changes. When they're not present, it's something else. And this difference here, the amount of time basically that the light is scattered away from the photodiode is proportional to the mass of the PM, of the particulate matter. So that's how the calculation sort of works. Another way of looking at this, basically, a similar schematic, you have your laser source, your laser, the air coming through, the measuring cavity, which is basically the photodiode. Oftentimes there is a amplifier, because the voltage changes measured by the photodiode are often quite small. So you can have an amplifier here to raise that signal. And that's what this third block here is. And then oftentimes there's also some kind of microprocessor that can do a little bit of small calculations to help process the final output. So these are very common, a couple of very common PM sensors. I'm going to focus mostly on the one on the left here, the Plantower PMS 5003. This is one of the most popular ones out there. If you've heard of Purple Air, these type of devices exist inside of Purple Air. That's what's actually doing the monitoring in the Purple Air. If you've heard of a Clarity monitor from the Clarity movement in California, they also use these. That's what's inside of Clarity. So this is actually in these various vendors' boxes, what is actually doing the measurement. So it's a very small device, looks just kind of like this rectangle. And then below it here is a bit of a schematic showing, what exactly is going on. And so it's similar to what I described earlier. You have kind of a photodiode and a laser. One thing that these sensors do is the sort of the geometry and the fluid dynamics of the flow. So as there's a fan here drawing in particles, and the larger particles are not able to sort of make these sharp turns through this chamber. So the larger particles get sort of filtered out, and what you're left with is mostly particles in the submicron range, maybe up to 1 or 2 microns at most. And so this makes these devices a pretty good estimate of PM 2.5. They will also report PM 10. In fact, all of these vendors report PM 10 and just basically entrust you to use it. However, for the reasons I just described with the flow geometry, the most 10 nanometer, or sorry, most PM10, most coarse particles that are greater than 2.5 microns and less than 10 microns aren't actually ever going to be observed by this kind of device. So this Plantower, and same thing with the Shinye, which is another similar type, are not good PM10 monitors. If there's any, aerosol above 2 or 3 microns, the Plantower is not going to see it. So, best practice would be, don't use these much for PM10. They are good for PM 2.5, and it can be a little deceiving because, Purple Air or Plantower or Clarity will definitely give you the data that they think is coming out for PM10 or even PM1. And yeah, you really, if you fully understand kind of the physics of what's happening here, then you know that those data are not super reliable. Bottom line, PM 2.5 generally pretty reliable with these devices. So this is a list of different manufacturers of low-cost sensors, different vendors, and a couple of different pieces of information and specs, hardware specs associated with each device. So some of the ways that they differ are things like the wavelength that the light is emitted at. So it's often a laser, and so the laser, operates somewhere in the red of the visible range. It's, most lasers are red, so it's somewhere in the red of the visible range, about in the plan tower, for example, about 650 nanometers. Other devices can use infrared. Certain devices don't actually tell you what wavelength their light is at. They just say it like laser or red laser. But you can see there's some variability here. There's also some variability in sort of the scattering angle. What angle things are the photodiode is oriented towards relative to the laser. And then also kind of what kind of flow do they have in the devices? So is there a fan or not? What are the kind of flow rates through the devices? Those are things that differ. There's also, different here about the particle sizes, that they can observe. None of them really tell you what the higher limit is. Most of them will tell you what the lower limit of detection is. And based on, it's somewhere around 300 nanometers or 0.3 microns for most low-cost sensors that act like nephelometers. So these type of devices are basically nephelometers. You can also see the various outputs here. Notice, as I mentioned, that a lot of these sensors will give you PM1, PM 2.5, PM4, PM10. The size distribution information that they provide is again is quite suspect. So don't really rely on PM10, PM1 for a lot of these sensors. So what about gas sensors? So we'll talk just briefly. Most of the work in this session will be on particles, but for gases, there's two types. There's either electrochemical sensors or metal oxide sensors. And the common electrochemical sensor that a lot of different vendors use is from a company called AlphaSense. And basically what an electrochemical sensor is that the gas molecules, for example, let's say you're measuring NO2 or ozone, those NO2 molecules or those ozone molecules diffuse through a selective barrier and then undergo an oxidation reaction on an electrode that allows a current to be created, and then that current can be converted into that signal can be converted into a concentration or a mixing ratio. So a lot of these sensors, can be cross-sensitive with each other. I mentioned NO2 and ozone. NO2 sensors are typically cross-sensitive with ozone, meaning that the signal will be the same, whether it's NO2 or ozone, and that can be misinterpreted. And so the NO2 sensor that AlphaSense makes, for example, has a little bit of an ozone scrubber, sort of a selective barrier that prevents the ozone from sort of getting through to the rest of the sensor and creating that electrical signal that then gets converted to mixing ratio. The other type of sensors, in addition to electrochemical, will be metal oxides. So metal oxide is basically your gas molecules, your NO2 or your ozone or whatever you're measuring, adsorb onto a selectively porous layer, and then change the electrical resistance of that layer, and then the resistance change can be converted into concentration or mixing ratio. So these are very tiny, 20 millimeters or so. These, you can see some pictures of them down here. And you can sort of see in the figure, there's a lot of different gases that they will claim to measure. And ozone and NO2, CO, CO2 are some of the big ones. And there's, like I mentioned with NO2, there's a lot of difficulties with cross sensitivities. There's also a lot of difficulties with sensor aging. So a lot of studies have found that for example, the NO2 monitors age, once the ozone scrubber is deteriorated and depleted, the NO2 is basically, a sensor is basically useless. And this is about typically after about a year or so. It varies depending on your environment and your concentrations, but these AlphaSense NO2 devices are really not meant to be used long term. So let's talk now about some things that can affect the way that these sensors detect particulate matter. And so basically anything that changes how light interacts with a particle will change the reading that you get from these scattering devices. And so some of the common ones are things like the humidity in the environment and in the chamber. Another one would be the size of the aerosol, the shape of the aerosol, the composition of the aerosol. And then another one is the sort of, I already mentioned this a little bit, but like the age of the sensors. So the older ones tend to age and deteriorate.
Yes, I'll join now.
Sorry if everybody can mute when they join. Okay, so this figure here is showing a little bit of how these different sensitivities work. And so let's start on the far left here. So a similar schematic as I showed earlier, you have your light source, some air coming through, and then the photodiode detector. So if you have no particles, there's no signal, nothing going on there. Let's go on the second case here. You have, sorry, please keep yourself muted if you're not speaking. Okay, so the photodiode here, for this middle particle will read, some hypothetical concentration here for this particle. Let's go to the third example here. And this is one way that low-cost sensors, in particular these nephelometer type low-cost sensors, can often fail. And that is, here we have two particles that are supposed to be about as massive as this one particle, but because of the way that they're oriented, you only have you have the photodiode sort of predicting a smaller signal than it would. So there's really the same mass of particles here, and the drawing was supposed to be meant that way, but because they're smaller, they sort of register differently. And then if we go to the next panel here, the similar thing for the shape of the particle. So let's say instead of having some nice spherical particles, you have this like fractal shape here. And what the sensor does there is complicated. It depends a lot on the exact shape, but either way, it's likely that you could have a different signal than you do with just the perfectly spherical particle. And then finally, on the far right, we have an example where the particles have swelled with water. So particles like to take up water. And here we have a smaller particle. So this black thing is supposed to be the particle. It's smaller than, for example, all these other examples, and therefore the photodiode signal you should be smaller because it's a smaller mass. However, because it has this water around it, that's going to change the optical properties and basically make the photodiode and the low-cost sensor think that there's a larger particle in there and sort of incorrectly estimate the mass. Okay. So that last point there about humidity is quite interesting, because this is one of the main ways that low-cost sensors can cause bias in their predictions of PM 2.5. So here we see on the y-axis here a ratio of the low-cost sensor PM 2.5 to the TOM PM 2.5, and the TOM is a reference monitor. And so at different relative humidities, you have sort of a different ratio. So you basically want a 1-to-1 ratio. That would mean that the low-cost sensor is performing as good as the reference monitor. And at about 40% relative humidity, let's say anywhere between like 30 and 60 or so, you're pretty good accuracy here. You're close to a 1-to-1 ratio. However, if you start to have higher relative humidity, go up to like 80% or so, you can see that the low-cost sensor tends to overpredict the reference PM by a factor of 1.5, 1.6, 2 in the most high cases of relative humidity, up to about 2. So this is an important thing to correct for. And the other, sorry, let me go back. The other figure here is showing the effect of particle composition. So a very similar plot. On the y-axis, we have the low-cost sensor PM2.5, and on the x-axis, we have the TOM PM2.5. And depending on what kind of composition you have, so for ammonium sulfate aerosol, which is typical of like coal-fired power plants, you can have a certain agreement. For dust, you might have a different agreement. For urban PM, which is just sort of a mixture of organic and inorganic aerosol, and then wood smoke, which is mostly going to be organic aerosol, you can see you have different predictions there. Okay, so going back to the humidity, just to show further that sensor accuracy is worse at higher relative humidities. This is some data from a paper by Mallings et al. A few years ago. And it's PM2.5 from the low-cost sensor on the y-axis, and PM2.5 from the reference monitor. This is in Pittsburgh, Pennsylvania, in the US. And so you can see that the agreement is fairly good, except at these higher levels of relative humidity. So the yellowish colors are the higher relative humidities, and you can see that the plot sort of deviates from the 1-to-1 line at those high relative humidities. So you have a mean absolute error of about 4.2 micrograms per meter cubed. We'll come back to what a mean absolute error is in a little bit. And you have some decent correlation. You can apply a very simple correction factor, which we'll talk about in more detail later, and get this figure on the right. So now we have the corrected PM2.5 on the y-axis versus the reference, and the mean absolute error has decreased by about half. So this was using a multiple linear regression correction factor, just using the same equation that's sort of down here, and we'll talk more about that in the in a few more slides. Gas sensors, gas phase pollution sensors also have interactions, and one of them is related to meteorology, of course. So similar to how humidity affects PM sensors, temperature affects gas sensors in a pretty strong way. And so this is some examples from an NO sensor, nitrogen oxide. And you can see that the uncorrected NO here correlates very strongly with the sensor temperature. So the green is the sensor temperature, the blue is the uncorrected NO2, and NO, and the red is the reference instrument. So you can see huge overprediction here. Also here is showing, a plot of the NO concentrations versus temperature. And you can see, there's a pretty tight relationship here. It's not exactly linear. It's, this fit is exponential, and it fits it pretty well. So besides meteorology, the other issue is with selectivity. So I already talked about this a little bit, but for example, NO2 sensors can be cross-sensitive with ozone sensors. So that can be a problem as well, when a sensor reacts to a gas that it shouldn't, basically, that you don't want, to measure O3, you want to measure NO2. Okay, I'll move on now a little bit to the next section. So this is talking about, do we have linearity in the sensor response versus the reference? So in each of those scatter plots that I was just showing, if we go back, for example, to here, we had pretty good linearity. This is the raw sensor data. on the y-axis and the reference data. And it's not a one-to-one line, but it's still, it's got an R of 0.76, so it's fairly linear. So this is sort of the ideal response. If the low-cost sensor has a linear relationship with the reference monitors, then you have some very easy, well, not easy, but you have some very good potential for getting high quality data out of these sensors. And as I mentioned, it doesn't need to be a one-to-one line. If it's a one-to-one line, then not only is the sensor linear, but it's also unbiased and therefore extremely accurate. And this is pretty rare. So the low-cost sensors, it's common that they have a linear relationship between the reference, but it's less common that it's unbiased at one-to-one. Some other things here that are not linear, but are still possible to deal with. If you have sort of more of a curve response, this is still correctable. You can still apply a model. You might not want to apply a linear model. You might want to apply a nonlinear correction model, since this hypothetical line here, this hypothetical curve here rather, is not linear. And then you can have some other types of relationships between the sensor values and the reference that are less likely to be useful. So if you have something that looks like either of these second two plots, it's very difficult to even use this sensor properly, even with some correction factors. So if you have data that looks like this third one or this fourth one, then you have kind of a suspect sensor, I would say. So, some takeaways here. We need to know how the sensors react to changing pollutant concentrations. We need to know if they have a linear response. We need to know over what range. Does the linearity change over the lifetime of the sensor? Is another question that can be relevant. So here again, most PM 2.5 sensors that I mentioned have shown to be linearly related to reference, all the way up to hundreds, if not thousands, of micrograms per meter cubed. Different sensors do respond differently in terms of what exactly that slope is. So there's some issues there. Electrochemical sensors, which are the types that are most commonly used for measuring gas phase pollutants, are also mostly linear as well. But the age of the sensor has a much bigger impact on the gas sensors than it does with PM, as I sort of mentioned earlier. Another thing to consider is the limits of detection. So we have both a lower limit of detection and an upper limit of detection. And most sensor manufacturers or most vendors will tell you this information. And they'll say, it's most of them will say it's kind of 1 microgram per meter cubed at the lower end, or 1,000 micrograms per meter cubed on the upper end. And they don't really give you any evidence or they just kind of say it and you're left to sort of trust them. So that's fine. I think, with at least with some of the common sensors that are used out there, like Purple Air and Clarity, that seems to be pretty accurate. But it's always good to be able to verify and test that. And so there's some methods here. You can use a HEPA filter to basically get a zero of particles, basically close to zero. The sensor won't consistently read just zero across the board. It'll probably deviate. You might have some negative numbers, but it'll be close to zero. And so basically one of the ways you can actually get the lower limit of detection is just by finding out, getting all that data, collecting it, taking the standard deviation of it, and then using the lower limit detection of at least 2 or 3 times the standard deviation. So if your standard deviation is something like 0.3 micrograms per meter cubed for a 0 filter reading, if you multiply that by 2 or 3, that'd be two times the standard deviation or 3 times the standard deviation. You're talking about something around 1 microgram per meter cube, which is generally what the sensors, the low cost sensors, report. Okay, let's go to the final section, and then we'll have time for questions at the end. So calibrations or correction factors are, one of the most important parts of all this, because you really shouldn't just be using low cost sensor data right out of the box, just raw data. So the goal here is to basically create a method that corrects the outputs of low-cost sensors based on some of those different factors or sensitivities that we mentioned earlier. So how do you do this? Well, you can, the tried and true method is just place low-cost sensors and reference monitors in the same location right next to each other and have them measure ambient pollutant concentrations for some period of time, long enough time to capture the entire range of the meteorological conditions or other source conditions in the area. There's not really a hard and fast rule for how long this should be. It depends on a lot of things. It depends on what kind of environmental conditions you have, but generally it is preferable to be able to sample, for example, multiple seasons, a long enough period of time that you can really span the range of humidity, temperature, and concentration. And this doesn't necessarily need to be done continuously. It could be a case where you co-locate it for a certain season for a couple weeks, go out and deploy it, bring it back in, in a different season, co-locate it for a couple weeks, send it back out. Something like that would be appropriate in certain settings. So this is, simple kind of schematic here. We have our reference monitor, in this square, and then the different low-cost sensors sort of around that during co-location, and then later you just go and deploy them, in these hypothetical areas. These are some important questions to consider. How long do I need to do it for? Do all the low-cost sensors need to be co-located, or only just a couple of them? Do you trust that each of the low-cost sensors are internally consistent with each other? Can it be done in multiple steps? So this is one thing I was just talking about, rainy season, dry season. Can the reference monitor moved, or is it fixed? This is another important question. So there's a lot of different ways to do calibrations. Let me just check the chat really quick. Okay, I see that there's some questions. Let me just, these are all good. I'll just come back to them at the end, if that's okay. So there's, we can do some simple methods like a linear or a quadratic regression. And these sometimes work pretty well. We can also have, more complex methods that require some coding experience, that use kind of machine learning methods. And, so basically this figure here is kind of the, what we're trying to do. So here we have the raw data in black. Sorry, the reference, the raw PM 2.5 from the low cost sensor is in black. The reference data is in blue. And so you can see between the black and the blue, yeah, there's a good bit of error there. There's a good bit of bias. The correlation looks pretty good, but there's a bias. So these methods, these calibration methods or correction methods, are basically going to give you this red curve, this corrected low cost sensor. And that's what we need to do. So the simple methods are simply just linear relationships. So you have, basically this is a multiple linear regression here. You have, y equals mx is sort of the simple linear version, but then you can add, other explanatory variables. So, x could be so if y is sort of the corrected PM 2.5, x could be the raw output from the sensor. P could be, for example, relative humidity. Q could be temperature. R could be like dew point or pressure. You can use a number of different variables. The question is kind of what variables do we use? And this is one particular paper's opinion about that, not necessarily the end all be all of this discussion, but they've listed here some parameters that they think are defendable and others that are sort of questionable. Relative humidity, of course, that one's pretty good. Temperature, those are all pretty standard. For gases, other gases for which cross sensitivity has been established. So what I was mentioning O2, if you have O2 and ozone, or sorry, NO2 and ozone, those could be included since they're cross sensitive. Here's some other things in here too. Yeah, so it's very sort of specific to your application. I would say, no matter what this table says, I think that for PM, the most common and the most useful other variables, input variables, would be, of course, the raw sensor data. After that, the relative humidity, and after that, the temperature. I think if those three are involved, then you're in pretty good shape. So, for PM sensors, that's exactly what I was just talking about here. So you have, your PM reference. A linear calibration model would be your PM reference is equal to some regression coefficient times the low cost sensor values plus another regression coefficient times the temperature values plus another regression coefficient times the relative humidity values plus the y-intercept. So these work pretty well. And I'll show some examples of that here in a minute. How do you validate your data? Well, you have to hold some data out. So you can do this, you build this model. The way that you get these slopes, or well, these regression coefficients, which in a linear model are sometimes called slopes. So like A, B, C, D is the y-intercept. You get those by training the model on the data that you have. And so if you're going to train the model on some data, then testing it on that same data would be sort of an unfair test. And so you need to hold some data out. You have this big data set. You need to hold some of it out to test the model independently against data that it has never seen, or otherwise it's going to be sort of a biased measurement. And so one way to do that is through k-fold cross-validation. This is what you do. Some data from the collocation is reserved or set aside, and this is the testing data. Something like 20% of it or 25% of it can be set aside for the testing data. The rest of it can be used to train the model and get those regression coefficients that actually build the model. The k-fold cross-validation is unique in that it picks a random 20% or 25% or whatever fraction you want of the data and holds that out as the test data, and then does the regression and the testing on that. And then it'll do basically the same thing again, but with a different 20% of the data. So it'll pick another random 20% of the data that wasn't, in the first 20%, and then do the training and the testing on that. And then repeat that until you've gone through all the data. So if you do a 20% holdout, then you're talking about five-fold cross-validation, because you can only have 20% chunks of data, in your data set. So a very simple example here is basically you have, let's pretend we have some kind of made up data here with the reference data and the low cost sensor data. And let's use these or actually, so let's take, how many data points are there? 1, 2, 3, 4, 5, 6. Let's take this red point here at the end and set that one aside as a testing data point. All right, so we're only going to build the model on these first 5 points here. So 1, 1.5, 4, 2.9, 7, 5.1, etc. So if you do that with just those black colored points, you get this relationship. And then, we didn't use this last one, this 24 and 23.7. We set that aside. So instead, let's predict what the reference value would be if we just use this model. So if you take this equation here, y equals a slope times x minus a y-intercept or plus a y-intercept. And let's put the low cost sensor. So the low cost sensor is the x value in here. If you put the 23.7 in here, you're going to end up with a predicted sort of reference value of 22.6. And so that can allow you then to estimate the difference between the prediction and the actual data. So the reference data should have been something like 24 because that's what our data point says. It was actually our prediction was 22.6. So that can give you can take the error from that, 5% error or something like that. So that would be doing it, with one fold. Now, if we did another fold, it's basically the same thing, except now instead of holding out this 24 data point, this last data point, let's hold out this second row here, this 4 and 2.9. So this is no longer in the regression. You get a slightly different equation, but not that much different. And then let's do the prediction. So if you have a low cost sensor of value of 2.9, you put it through this prediction model, you get an output of let's call it 3.5. So again, pretty close to 4, and you can calculate the error. So this method is the same, no matter what model is used. If you use a more complex linear regression with multiple variables, it can be sort of similar. So this brings up the question: how do we evaluate model performance? And there's a couple of ways to do it. One is by looking at the bias, and one is by looking at the correlation. So on the right here, these values are, you'd say highly correlated. So you have, for example, concentration versus hour of the day. The true NO2 concentration or the reference would be in blue. You can see it's very highly correlated. However, it's a little bit biased. It has a mean absolute error or a root mean squared error, of some that's unacceptably high. You can see this is indicated here by these, the difference in this data. So, a couple of different ways of looking at this. Mean normalized bias gives an impression of the long-term accuracy or stability of the measurements. Lower bias is better. Pearson R, or you can also do R squared. It's a measure of the correlation. A higher R squared is better. Bias corrected coefficient of variation of the mean absolute error, CVMAE. This is a measure of the precision of the model, so the bias, but it's also normalized by the mean and corrected to account for different scales of gas and PM concentrations that the models are built on. So here a lower bias is better. So if you have a plot like this, you can have the CVMAE on the y-axis and the R on the x-axis. Notice the R is reverse. The ideal zone for your low cost sensors is down at the bottom left. So just looking at this in practice, this is some results from a paper from my group in Kinshasa in the Democratic, no, sorry, this is in Kampala, Uganda, where we co-located a purple air at a US Embassy reference site. And so the purple air is in purple. The reference data from the US Embassy is in orange. And you can see there's a huge difference there. So the purple air is highly correlated, but high biased. When we apply this simple linear regression correction factor, we get this turquoise or blue line. And you can see the blue line now is tracking really closely with the predicted, with the reference. These are some of the statistics. So, the raw purple air data, depending on if you daily or hourly averaged it, it had something like 15 to 20 micrograms per meter cubed of mean absolute error. This is in Kampala for these dates. If you apply a multiple linear regression, that mean absolute error reduces to about 3 for the daily average and about 7 for the hourly average. So this simple multiple linear regression, method is quite powerful. It can reduce your bias from something that is, not very reliable to something that can be, useful in a lot of different settings and is almost close enough to, reference quality data. This is in Ghana, so we did something similar there. You can see some of the results here. And in the interest of time, I'll just move along. Let's look at gases a little bit here. So for CO and O3, these are typical gases. The models, again, you want to be in the bottom left of these plots. If you're in the bottom left, that's an indication of a good sensor. So these data points down here on the O3 and also down here on the CO are performing pretty well. And these points are including linear and quadratic regressions. The neural network performs pretty poorly. The Gaussian process performs pretty poorly. But the random forest, which is a machine learning method, and the linear regressions seem to perform pretty well for both carbon monoxide and ozone. And then similarly here, for NO, no models really do a good job of predicting NO. This is a really tough measurement. NO2, you do get slightly better performance. And here the machine learning models work the best. So with that, I think I'll wrap up and take a look at some questions. I'll just leave these final thoughts here. There's tons of ways to use low-cost sensors, and we simply need to understand the caveats and use them mindfully so that we can get useful data out of them. So I'll stop there and take your questions. Okay. So I guess, if anyone has any questions they want to just go ahead and ask, then, feel free to keep them typing in, but I'm going to start going through the ones in the chat. And we'll start at the top. This is from Collins. Question, please. Does that mean that through temp and RH effects have to be corrected for, we should be more concerned about relative humidity for PM measurement? I think the short answer to that, Collins, is yes. I think that relative humidity has a stronger influence on sensor performance. Certainly the aerosol physics of humidity and water uptake by particles is more relevant. Temperature can also affect things as well, but I think that relative humidity is probably the more important factor. Okay, and then we have Dr. Hughes from Ghana. What radius of coverage do these sensors account for? 1 kilometer, 10 kilometers? I would say that that's 1 kilometer is too long, too much of a radius. Much less than that. It's tough to say exactly because it depends a little bit on, for example, the height of the sensors. If a sensor is placed at ground level or close to ground level, it's going to be more directly impacted by the immediate, vicinity emission sources. You know, like if somebody's operating a barbecue stove nearby, if it let's take the opposite of that. Let's say it's located on the top of a 4-story building. Then, you know, those little ground sources they're still there, of course, but they're not going to really affect that measurement that much because, you know, there'll be dilution and mixing by the time that plume from that, you know, barbecue stove reaches the 4th floor sensor location, if it ever does even reach the sensor location. So if you have it higher like that, you can probably be more confident in the representative range of the sensors. I don't really have an exact number. I would say 1 kilometer is probably much too high. I'd say, you know, probably tens or hundreds of meters would be something I'd be more comfortable with. But it's really kind of it's an open question. I'd say it's a really good question. It's one that a lot of people get asked a lot. So, you know, I think we're still kind of struggling with that question. How dense should sensors be deployed? So this is from Mr. Oppo from EPA Ghana. It really depends on your question. I mean, if you want to know like the hyper local and neighborhood scale differences in PM 2.5 from one street canyon to another street canyon, then obviously you need dense sensor deployment everywhere. You need it at that level. But if you're interested in just sort of the overall citywide, you know, concentrations, like let's say you just want to get a overall survey of what, you know, the air quality is in a given city, you don't need really that many. I mean, I could see 10, 20, something like that. The key is that if you do that, then it's wise to deploy them in places that give you a nice representation of the sources in that city. So you would not want to have all 5, 10, 20 of them at roadside locations where they're just all the time getting, you know, what's the word? Impacted by fresh emissions. You would want some in sort of the background locations, you know, maybe in like a cleaner area so that you can sort of get an overall picture. Yeah. Question from Bernard from Ouagadougou. Can I use T and RH from the LCS measurement? Yeah, that's a good question. I forgot to mention that. Yes, you oftentimes when we're talking about the temperature and the relative humidity in these correction factors, what we're actually using is the temperature and relative humidity as reported by the low cost sensor. So it's actually, you know, in terms of temperature, it's actually the temperature inside the sensing chamber rather than the outdoor temperature, which can be slightly different. Question from Jessica Puraz. What's hidden data? I'm not exactly sure what you're referring to there. Are you able to unmute and explain that question a little bit more? And I'll try to answer it.
Can you hear me?
Yes.
Yeah, sorry, thank you for taking my question. It was in one of your slides, I think, when you discuss or you show calibration calculations. I'm a sociologist, so I'm not really well aware about all the technical things, but at some point you put in a sentence hidden data.
Oh, yes. So what that was referring to is, yeah, that's sort of a confusing terminology. Sorry about that. What that was referring to is the testing data. So remember we were talking about the cross-validation, and I was saying use 80% of the data to train the model and then set aside 20% of the data to test the model. So the hidden data was referring to the stuff that was being set aside. So by hidden, what it means is hidden from the model. So the model doesn't see it, and therefore when it's tested against it, it's sort of new. That's a little bit confusing terminology, but that's sort of what I meant. Questions from Collins. What influences which data set to hold to test the model? Okay to pick any data set at all. I think the best way to do it is to do it randomly. So, and it doesn't necessarily have to be a continuous, you don't have to say, I'm going to take all the data from April 1st to April 15th, it can just be sort of random. I think the most fair way to do it is to do that randomly, and that way you get the most possible, I'd say the most unbiased test of the model. And a question from Mr. Uppo. You have been talking about models being used. Which of them suits our environment? I think the linear regression has worked very well in many different papers. I think in terms of places to start in Africa, we should probably start there. We should start with the linear regression that uses temperature, relative humidity, and raw sensor data as the input variables. To me, that is the most logical place to start. It's probably the most reproducible as well. So it's easier for people to implement. So that would probably be my answer to that.
Then probably,
Yeah.
if we really want to add the climatic variables, would that work? That one as against the multiple linear regressions, which one would be far better? Because if you want to include the climate.
Yeah. Oh, I think I think the variables you want to use are probably just, humidity and temperature. I wouldn't really add too many meteorological or climatic variables besides that. The more variables you add, you could get better performance, but you also run the risk of overfitting your model. So you run the risk of like building a model that's just really, really specific to, one data set and not representative, and so not as useful. Yeah.
Again, you talk of using the temperature and humidity from the sensors.
Yes.
We know that the external influences are much greater than from the sensor. So if we have temperature and pressure and humidity from the National Meteorological Agency, can't we use that instead of those from the sensors?
Oh, I see. You could, but I think the better thing to do is to use what the sensor is reporting. The reason for that is because that's the temperature and the humidity that are inside the chamber of the clarity device or the purple air or whatever. Those are the temperatures and humidities that are actually affecting the scattering and the measurement. And so, I think that makes more sense to use than the ambient temperature and humidity, for example, that you can get from, meteorological agencies. They probably don't differ all that much. And it can be an interesting exercise to compare those data. But yeah, I think to me, it makes more sense to use the internal measurements, because that's what's affecting the particles.
So what would be the variation between the reference monitor and that of the local sensor? Because they may behave differently. So if you're looking at the temperature in between them, that's why I'm asking if you can use from a more reference source than the local sensors.
Yeah, I mean, again, I think the best thing is to use what's in the sensor. I mean, you can compare like the Teledyne's temperature output to the purple air temperature output, and it's probably going to be similar. It really kind of there's a lot of different temperatures associated with the reference monitor because there's oftentimes climate control. So you have to make sure you're using the right values. But I think that I think it could be an interesting exercise to compare the two, but I still think that the best method is to use what the sensor is reporting.
Okay.
Yeah.
Okay.
Dr. Hughes, there are numerous sensors for sensing both PM and gases. What determines the choice of sensors for deployment? Yeah, that's a good question. It's sort of it's up to the individual a little bit. I think, price is probably something. Performance, some sensors work better than others. And, I think that, Dr. Hughes and Mr. Oppo and folks in Ghana, we're kind of looking at that right now with the sensor intercomparison project there. But yeah, I mean, to me, the thing that matters the most is performance. I don't want to buy a sensor that is just going to give me junk data. There's some other factors like connectivity is sort of an issue. So, do you need a solar panel? Do you need cellular upload? That can be a problem with like the purple airs. The purple airs don't have solar. It's just plug into the grid. They also use Wi-Fi to transmit data. So there's a lot. I mean, there's a lot of different factors. Yeah, it's a good question. And then Collins, does aerosol buildup affect the correction factor developed from one region to another? Yeah. So there's kind of two parts to that question. One, it depends on what you mean by region, but like generally most correction factors so far have been designed for a rather specific region. So you wouldn't necessarily go taking correction factors from the US and applying it in Ghana. So that's one part of the question. I think the other part, aerosol buildup. Yeah, so the concentrations definitely impact the performance of the sensor. In some cases when you have really high polluted cities and you have sensors there, the optics can be impacted. So you can get, you get errors in your sensing, and then you need to go back and either replace the sensors or just calibrate them again. And then Bernard, can we have this presentation? Yes, I will send it to Mike. I don't have the email list for everybody, so I'll send it to Mike Giordano, and then he'll send it to everybody else. All right. So I think maybe we'll stop there because it's already 12:15. If you have any more questions, let me put my email in the chat. I think I already know that a lot of you have my email already, but just in case you don't, that's my email address. I just put it in the chat. Feel free to shoot me an email, and we'll go from there. Thank you very much. And Bertrand, is there any final words that you want to wrap up with?
Yes, yes. Well, I want to tell the participants that there might be another session, other sessions on LCS, because this is the first one, and there will be maybe 2 or 3 others in the upcoming month. We have to arrange that with Mike. I want also to tell the participants that there will be a session maybe in June on LCS in French. we are still going to arrange that with Mike also, and maybe with colleagues from Cote d'Ivoire. We have to arrange that, and then we will send out the announcement when this is clear for us from our side. So I want just to remind also that on Friday we will be discussing air pollution in West Africa, as I said, with few colleagues from Togo, from Senegal, and from Burkina Faso. Okay. And last thing I want to remind us that also that we have this conference, and we want to have to invite all participants to send their papers. And I would say also that the registration is free. So we welcome all papers from all researchers and from all disciplines. That's it.
Okay. All right. Thanks a lot. Sounds good. Thanks for coming, everybody. And we'll see you next time.
Au
Thank you.
revoir.
Bye
Au
now.
revoir. À bientôt.